Let's see if it works. How do I get that other? This one? This one? Ooh, is this one? Turn this off. Let's turn it to here. No input is detected. How do you turn off the projector? There. It's working. God. Sometimes I amaze myself.
Not seeing you.
Can the Zoom folks hear me okay?
Yes, we can hear you.
Can you hear me?
Yes.
I can't hear you. This is not good. Oh, I can't hear you. Oh, I can't hear you. I can't hear you. Why not? I can hear you. You can hear me, but the other person can't hear me? Okay. Why doesn't
Can't hear
somebody
you,
say
Professor.
something? Can you guys unmute and talk? No?
We can hear you.
Yeah, we can hear you.
All right. Well, maybe if you are able to text, it'll pop up and we'll see it. So if you have a question, we'll be able to, someone in the classroom will notice it. I've got you projecting onto the video screen, so your texts will come out. And if you have a question, you could just text it. I don't know why we can't hear you. Oh, I know why. It has something to do with the audio of the room. The audio of the room. I don't know how to turn the audio of the room on. Okay. It's a mystery. All right, so the audio of the room is not working, but you can text, so we'll be able to hear that. Apparently the audio is routed to the Apple TV. Who would have thunk it? Welcome to another exciting hybrid distance learning computer architecture class. Looks like we have a few enough people here. 1, 2, 3, 4, 5, 6, only 6? If we keep going at this rate, maybe I'll combine the two sections and we'll still be able to do social distancing, because it seems to me like there's room for perhaps 15 people to do social distancing in this classroom. More people are coming in, so that's good. So I'm going to open the floor to questions about homework number 1. This was the midterm that I used for one of my digital design classes. Did anybody have any questions about this midterm? If you're doing distance learning, you can certainly pop the question up in the chat. We won't be able to hear you because I can't seem to get the audio to work for the Apple TV. No questions?
Can we go over?
The ginormous homework 1? No questions. There are 46 pages here and nobody has any questions. Oh, somebody does. Can we go over 29 and 30? Sure. Sure we can. Okay. 29 says, an overflow condition, it should say, occurs whenever the sum of two positive numbers yields a positive result. Is that true or false? That's false, right? If I add 1 plus 1 and get 2, that's not an overflow condition, that's normal. So adding two positive numbers doesn't necessarily create an overflow condition. That's obviously false. So 29 answer is false. When do you have an overflow condition? Anybody know? Yes.
When two negatives add both positives or positives add to negatives.
Sure. If you sum two positive numbers and you get a negative result, that's an overflow. If you sum two negative numbers and get a positive result, that's an overflow. Then number 30 is taken straight out of the CATS book. And so if you have an opportunity to look at chapter 5 in CATS, this is contemporary logic design, you should be able to see how this is implemented. And I believe they put in an exclusive or gate. So in case you're wondering, that's just another little half adder, and that's going into question number 30 as the answer. It's B. Let's do one sort of ad hoc little explanation about exclusive or. So this is the truth table for exclusive or. How can we describe what exclusive or does in words? Go ahead.
It's one or the other.
One or the other. One or the other. That's interesting. I hadn't thought about it like that. Yes, sir.
That, but also not both.
Not both. Okay. How about if A is not equal to B? If A equals 0 and B equals 0, they are equal, and therefore you output 0. If A is equal to 1 and B is equal to 1, they are equal, therefore you output 0. So when A is not equal to B, then you output a 1. What would be the, let's say, C or C++ or Java or C# implementation for a bitwise exclusive or? Bitwise exclusive. So let's assume integer I is equal to binary, this would be in C, 0, 0, 1, 0. Integer k is equal to b, 1, 1, 1, 0. How would I express bitwise exclusive or between I and k? I'll write it this way. Integer j is equal to, and now I want bitwise exclusive or. Yes. Yes, a caret. So I caret k gives me a bitwise exclusive or. Now let's assume that exclusive or is the same as not equal. What would be the Boolean logical equivalent for not equal? Let's assume we have Boolean. Let's say B sub I is equal to true. Boolean B sub j is equal to false. How do we do Boolean B sub k? So that B sub I is equal to the logical exclusive OR between B sub I and B sub j. Yes?
Not equal sign.
Yeah, not equal. So I could say B sub I bang equal B sub j. So that is the Boolean equivalent of the bitwise exclusive OR. Suppose you wanted to do a bitwise inclusive OR. Bitwise inclusive OR. This is exclusive. Inclusive is a OR bit, right? So that's just like the normal OR. How do we do a bitwise inclusive OR? We'll call it IJKL. Integer L is going to be equal to the bitwise inclusive OR between I and K. Inclusive OR. Anybody out in Zoom land want to chime in? I'm not seeing anything. Inclusive OR is done this way. I vertical bar K. That's inclusive OR. So now that will give us a bitwise inclusive OR output, which would be equal to B in this case. Well, into K. In other words, L would be equal to K after this is done. Suppose I wanted to do a Boolean inclusive OR between B sub I and B sub j. How would I do that? We'll call it B sub L equals, what do we write? Zoomland people, you can chime in. Zoomland, can you hear me, Zoomland? Take off the mask and risk infecting the class. Can you hear me, Zoomland? I hope they can hear me.
Yes.
Yes, okay. How would I do an inclusive OR between B sub I and B sub j using the Boolean logic, not bitwise? Inclusive OR. And this is true for C and C++ and Java and C# and .net or yes.
Double ampersand.
Yeah, a double vertical bar. You were close. Double ampersand would be an and. Double vertical bar is an or. So it would be B sub I, double vertical bar, B sub j. And the output from this would be Boolean, and you could do a Boolean assignment.
So what was the difference between the single vertical bar and the double?
One is a logical argument, and the other is a scalar argument.
Oh, that one.
Yeah, this one is a scalar argument. So these two scalars would be something like 8-bit bytes or 16-bit shorts or 32-bit ints or 64-bit longs. It would not be floats. That would not work. But or even chars, it would work on chars. So in the case of bitwise inclusive OR, you could set a bit. So in the case of, let's say, the American Standard Code of Information Interchange, which is an 8-bit code, the difference between lowercase and uppercase letters is 1 bit. So you could set that bit and convert everything to uppercase, or you could clear that bit and convert everything to lowercase. And that's a very efficient way to lowercase ASCII, American Standard Code for Information Interchange. Yes. And in fact, the least significant 8 bits on Unicode in English and Java is ASCII. But if you're going to use a full-blown Unicode 16-bit character that no longer applies. For example, you could have a 16-bit representation of an ideographic language like katakana, and that would not work. You don't have the uppercase, lowercase thing that the ASCII has. Are there any other questions about homework number 1? Going once? Going twice? Oh, all right then. So we went through 46 pages, right? And no questions, because it's all obvious. Right? Obvious. So what I thought I would do, since we're in the middle of review stuff, is have a little discussion about some of the stuff that we would have done had we remembered chapters 8 and 9 out of our CATS book, Contemporary Logic Design. And so what we'll do is we'll talk a little bit about finite state machines, and we're going to use that for designing our computer architectures. So we're going to build on the stuff that we learned in our Digital Design 1 class. So it's all very exciting. I can see you guys are excited, right? Good. It is very exciting. Very exciting. So let's see what we can do about that. I am holding here in my hand one of the most inexpensive, I almost said cheap. Okay, cheap. One of the cheapest watches you can buy. It's a Timex. It is really a wonder of mass-produced technology that you can buy these things for under 20 bucks. And what I do is I beat the crap out of them and throw them away and buy another one. I'm very hard on these commodity watches. I actually have good watches at home, which I wear on special occasions, but for my everyday stuff, this is what I wear. The Timex watch is a very interesting watch. Because of its mass production, it doesn't have anything particularly expensive inside of it. In fact, I think the reason why it's such a successful watch is that it's a reliable watch that seems to work reasonably well for a long period of time and is extraordinarily cheap. People like to spend very little money on things like this. Now, can you make them more expensive? Sure. I could gold plate it, or make it out of solid gold, or maybe I could make it out of diamonds and rubies and all kinds of interesting and wonderful things. But if you choose to just make it out of commodity stainless steel and make it as cheap as you possibly can, they come out cheap. And people like cheap. I like cheap. It offends my sense of thrift to have a gold watch that I wear every day, especially if I bang it up and get it all ruined. So this movement that it has is powered by a stepper motor. That's what it does. It just steps one step at a time, once every second, tick tock, tick tock. That's how this watch works. It's a stepper motor. Stepper motor is a very interesting kind of motor. It has what I would call a digital design friendly interface, right? What is a stepper motor? Can anybody tell me? Well, okay. What's a motor? Yes.
Motor is something that takes in energy and reuses it for something else.
Well, let's put it a different way. If you had a machine, by definition, a machine is anything that converts energy from one form into another. So I could have a battery that takes chemical energy and converts it into electricity. That's a machine, but it's not a motor. A motor is a different kind of machine. right? I could have a human being that consumes 2 teaspoons of sugar per hour and oxygen and food and converts it into lectures that everybody seems to enjoy. Right? Aren't you having fun now? So as it happens, human beings are kinds of machines, right? They create mechanical motion and sound and other things, electrical energy, all from chemical energy. So as a result, human beings are machines. And we must admit that human beings think, or at least they think they think. That's an important distinction. And therefore, machines must think if we define machines in this way. And so then the question is, you know, what kind of a machine is a motor? You guys, some of you drive. You drive to work or to class in a machine, which you call perhaps a car or a motorcycle or your hovercraft or whatever it is you use to get to work. It has an engine. What does it do? Anybody in Zoom land knows what a motor does? A motor creates mechanical motion, right? So motors are responsible for motion. And we define the kind of motor that we have by the input, right? So if I have a Tesla, maybe I have an electric motor because the input's electricity, but actually it's chemical energy from the battery. And if I have, I don't know, a regular car that uses gasoline, I have a gas motor, gas engine. If I have a watch, right, I could probably make it run on the battery, which is really chemical energy, but the input to the thing most directly is going to be electricity. So when we're dealing with microcontrollers, it's very typical for us to deal with an electric stepper motor. I could probably make one that runs on diesel fuel, but that's not normal. We'll say the social norm for stepper motors, they're electric motors. So, and they input electricity and they output motion. That's what motors do. Generators are different. Generators input motion and they output electricity. So in fact, a generator is just a motor backwards. And many electric DC motors, if they have magnets and coils, will actually be able to be used as alternators, and they can output, or magnetos if you like, they will output DC electricity or AC electricity, depending on whether they're magnetos or alternators, and they will output those things as a function of the motion putting into them. So you put motion in and you get electricity out. That's how hydroelectric plants work, right? They take the motion of the water going through the turbines, and they turn them into electricity, which they run through a power line. Well, windmills, right? All those windmills that are turning in the Midwest and actually in many states, including this one. Well, they're taking motion and converting it to electricity. So a stepper motor takes electricity, converts it into motion. And we like these things because they have impact on the surrounding environment. We call them actuators. So there's the stepper motor. And what we like to do, because it's digital design friendly, is we can input the instruction to step. And it will run one step. And this instruction can be timed in a synchronous manner using a clock. So when we look at the clock inside of my Timex, they call it a quartz watch. It has essentially a crystal. Which runs at 32,768 hertz, goes into a divider, which is really a little more than a counter with 14 bits in it. That's in this watch. And then goes into a stepper motor, which then drives the sweep second hand that causes what they call the movement, right? And it counts out the seconds. This is running at, this is a divide by 15. Because 2 to the 15 is 32,768. So once per second, we get a step, and then this goes in and drives the movement, which is the sweep second hand, which is geared to the minute hand, which is geared to the hour hand, and that is geared to a little thing that does one of the complications known as the date. So it changes the date once every 24 hours. What does it mean when they say that your watch is jeweled and it has 17 jewels? You don't see any jewels when you look at it. What does it mean? You know this? Well, what it means is they've used rubies, which are extraordinarily hard. These are sapphires, and they grind them down so there's a little pivot point, and they are used as the bearings for the movement. And so that reduces friction inside of the watch. So a lot of times watches are wearing down their internal movements because they're constantly in motion. So people use extraordinarily hard elements. Sapphires are generally harder than diamonds. You know, people say, oh, diamonds are the hardest thing, but they're not. It's rubies and sapphires that are the hardest thing. And so you can create industrial sapphires. They're not particularly valuable, but they're useful. And they use them to make bearings inside of the movements for the watches, and that allows them to operate smoothly. You don't have to oil them. Stepper motors. What's the other kind of electric motor that we know? Well, a stepper motor is operating with a complicated input using perhaps 4 poles. Right? And this multi-pole motor is controlled either through a digital design circuit or directly from a microcontroller with software to allow it to effective rotation. And it takes the poles, energizes them, and causes the part that moves, right? There's a part that stays in one place. They call it the stator. There's the part that moves. Oftentimes it's in the side, but it doesn't have to be. For drones, it's on the outside. And that's called the rotor. So motors, in general, have 2 parts. The part that stays is the stator. That's linked to the housing that's somehow anchored to the chassis. And then there's the rotor. The rotor does the rotation. The stator stays put. And so a lot of times what will happen is you'll have a different style of motor that doesn't use the computer to drive it like the stepper does, or some digital design circuit. Instead, it is what's known as a simple DC motor. Yeah, all right. Clearly, with the Zoom audience. DC motor. DC motors are different. Why? Because you add some sort of power to the DC motor, such as a voltage, and it will spin up. And if you want it to go faster, you increase the voltage until eventually you burn out the motor. But it's nice if you have a DC motor with variable speed, because what you'll do there is, if it's like a power drill, you'll hit this trigger slow, and then if you want it to go fast, you squeeze the trigger hard. Let's take a look at some of this interesting stuff. How do I design a DC motor? Yes, sir.
Well, you'll need, depending on the type, you might need brushes, you might need a commutator.
Yep.
You'll need magnets.
Yep.
For electric.
true. All true. So if in the stator we have a magnet, we'll call this one north, and then another magnet over here, which we'll call south. So we're putting the magnet now on the outside. We don't have to do that, but we could. Then inside, what we're going to have is electromagnets. And the electromagnets will be polarized in one direction and then in the other direction. And they'll go into the rotor around a shaft. And we'll, yes.
Sorry, the Zoom people said they can't see the board.
Oh. I'm gonna actually, yes. I'm gonna make a mark to remind myself about the extent to which we can see. Yeah, I'll just keep things inside of the frame. There. So can you see okay now? You're right. So here comes two coils. They're spinning around, and they're going to spin so that they can repel the southern side and attract the northern side during the spinning process. And to change their polarization, what we'll do is we'll alternate the direction in which the current goes inside of these coils by using what's called brushes. So the brushes could be as simple as a couple of metal contacts that lean up against the rotor, because what happens when this is spinning around, if you were to hook it up directly, you would twist the wires and break them. So what you need to do is you need to have a conductive strip, which is not touching the other conductive strip, and then that will energize this coil and then energize the alternate coil in a different direction. That'll turn because of some electromotive force from the battery. Sometimes you have to give these things a starting spin to get them going. So that's a DC motor. So we have completely different motor designs, one for stepper motors, one for DC motors. And we can build finite state machines in order to be able to drive the motors themselves. So then the next question is, okay, what's a finite state machine? I'll go you one further. What's a counter? Let's see if we can just sort of review these two basic ideas. Okay? Counters versus finite state machines. What's the difference? What's a counter? Yes, sir.
Something that keeps adding on to the previous value.
Adds on to the previous value. So 3, 2, 1, 0, blast off. Is that a counter? So it's not adding on, it's subtracting. So that's still a counter, right? How about 1, 2, 4, 3? That's not adding. Is that a counter? It's not even going sequentially. 1, 2, 4, 3. It repeats. 1, 2, 4, 3. Is that a counter? The answer is yes, it is. It is a counter. It is a counter. What about this one? 1, 1, 2, 3. And repeat. Is that a counter? And the answer is no. It's not a counter. Well, what's the difference? Yes. Yes, if there's repetition, it's a finite state machine, not a counter. If there's no repetition, if you visit each one of the states once and only once in the sequence. You don't have to visit them all, but here, visiting these in a sequence, then you have yourself a counter. Finite state machines are characterized by a finite number of states. All counters are finite state machines, but not all finite state machines are counters. So a counter is a degenerate finite state machine. It's degenerate. Are you guys familiar with the term synchronous? Synchronous. I guess maybe what we're doing is a really basic sort of review of some of the concepts, which I am sure you already know. But let's just do it anyway. Synchronous. What does synchronous mean? And you folks out in Zoom land, you can participate too. Yes, sir.
Something that happens at the same time.
Yeah, in time. So who was Kronos? Anybody remember Kronos? Yes.
Like Greek god.
Yeah, a Greek god of time. The Greek god of time. He used to have a scythe, which probably meant he could get a seat on the subway. There was an Egyptian god of time, the corresponding god of time. Anybody know what the name of the Egyptian god is? It's Horus. Horus and Kronos are practically the same person, but Egyptians called them Horus and the Greeks called them Kronos. If you go to Whaley Avenue in New Haven, you'll find a guy who makes clocks and fixes clocks. And on his front, the storefront, it says he's a horologist. They don't call them chronologists because those are people that sound like historians. He's a horologist because he's a person who fixes clocks. And when something is synchronous, it's said to be in time. And when something is asynchronous, it's said to be out of time. Out of time. When you have a finite state machine, it can be synchronous. And if it's synchronous, what that means is its outputs change in accordance with a clock. And so what you get is some combinational logic block, right, driving some storage device, what we call state memory. Could be something as simple as a bunch of D flip-flops, a register that can latch, right? And so the combinational logic block drives the state memory and is driven by some number of bits for input, right? So there's input to the finite state machine. Moreover, there is a clock which tells the state memory when to start to sample the combinational logic block output. There's the clock. And then the state memory is fed back. Some part of the state goes back into the combinational logic block. And then the output of the state memory, that goes to another piece of output logic, which we'll call G, output logic. And then that gives us our output. And that, because this G will only change when the state memory changes, which will only change when this clock changes, makes this synchronous. That's synchronous. And there are two kinds of machines, finite state machines, synchronous and asynchronous. This is the synchronous kind. The synchronous kinds, these are called Moore machines. Is any of this coming back to you guys? Does it sound sort of familiar? Synchronous more machines. What's the other kind of machine? It's an asynchronous machine. What do you call it? Does nobody remember this? Yes. Yeah, Mealy machines. Thank you. So Mealy machines are the alternative way in which you can design these machines. And what Mealy machines will do, I mean, really just like the Moore machine with a difference. And the difference is they'll provide a bypass on the state memory. So if there's an asynchronous change on the input, you can get an output right away. So this is the part that corresponds to the Mealy machine. That makes it a Mealy. And it makes it asynchronous because now it's only changing with respect to the inputs and the state. So you can have changes that occur just by virtue of the fact that you've got some interesting inputs. So this is chapter 8 in the Contemporary Logic Design book, which hopefully everyone has. And if you don't, I have extra used copies available for you I can bring in. I did that the other day for a student who didn't have it. Why would somebody use a Mealy machine instead of a Moore machine? If Moore machines are synchronous and Mealy machines are asynchronous, and synchronous, it sounds like a good thing to have. Why on earth would I want to use a Mealy machine? Yes. Any question? Any ideas? Well, the Mealy machine typically has fewer states. Typically fewer states. Mealy machine can react right away with a change in input. So if you remember your string recognition designers, they could output a signal that indicated they found the string right away, just as soon as the bit appeared, long before a clock comes in. So Mealy machines have a certain advantage in simplicity and in speed. But synchronous machines have an advantage too. They have a single source for the clock, and you know exactly when things are going to change. And that kind of is an advantage. It's a big advantage, actually. And what about this combinational logic block? How can we implement that? Let's assume I already know what the truth table should look like. What would you do to implement a truth table? You all took Digital Design 1, right? How did we implement truth tables? Suppose you wanted a minimal sum of products. What would you do? K-maps, sure. Or you could plunk it into your Quartus system and have it do an optimization. But suppose you wanted something more general. You could use a programmable logic device, like an FPGA. Or the ultimate programmable logic device, you could use a ROM. So over here, you could make this into a read-only memory, or even RAM, read access memory, any kind of memory. And this could just serve as a lookup, driving your state machine. Similarly, you could have this programmable, also with a RAM or with an FPGA. And then all you have to do to change the nature of the machine is upload new data to your RAM or your ROM. So at this point, what we've done is we've done questions. This is homework 2 now I'm looking at. Questions numbered 1, 2, and 3. That's what we've gone through so far in homework number 2. And one of the things that I did was I lifted homework number 2 from a prior edition of this course, and I found out that many of the pictures were missing. And so I have to go back and try and replace them. And as a result, I did not release homework number 2 just yet. Homework number 2 should be due at the end of the day on the 10th. I think that's a Thursday, isn't it? Do people know when homework 1 is due? It's due this week, I think. It's due tonight?
Homework dues due
Homework 1 is due tonight? All right, so I got to get homework 2 out there.
Is that homework that second?
Right, because we had our first class a week ago,
I'm sorry, quick question, Professor.
so it's due in a week. That's cool. That's cool.
Professor? Professor, is the second homework due next week?
Let's do a finite state machine diagram. This will be from number 5 and homework 2. And what we'll do is we'll just make this into a little bit of an example.
Professor? Professor?
There. Let's assume for the moment that the input is 1, 2, 3, 4, 5, 6 ones. What will the output be? First of all, is this a Moore machine or a Mealy machine? Moore machine or Mealy machine? Any ideas? Okay, so one thing we know about Moore machines is they have a synchronous input with a synchronous output. They are characterized by having their output written as a function only of state. So if you're in state 1, you're going to have an output only from state 1. It's not going to be a function of the input at all. So we're looking at these states and we see the input is on the top, the output is on the bottom. That's how we draw it. Looks like to me, this is a Mealy machine. Why? Because the output is a function of the input and the state. Therefore, if the input is changing, the output can change right away before you get to that state. So inputs trigger a state change, and at the same time, they change the output. So that's a Mealy machine. This is an asynchronous machine. It's driven by its input, not by its clock. So let's take a look there. If you're in state 0, and you get a 1, you transition to state 1, and you output a 0. Then you get to another 1, you're in transition to state 2. and your output is 0. You get another 1, you transition to state 3, and you output a 1. And then you keep outputting a 1 until you get a 0, in which case you go back to state 0, and you output a 0. So then you go from state 0 to state 1, output is 0. State 2, output is 0. State 0, you go back. And then 1, 2. On the third one, you output a 1. The next one, you output a 1. And then you're getting a 0. Now you're back to state 0. You got a 1, that's a 0. And another 1, that's a 0. You have another 1, that's a 1. Yes, sir.
The state 0, should the 1 on the left be 0, 1, 1, 0?
State 0?
Yeah.
Should this be 1, 0?
Should it be 0, 1? Because it has 2 input of 1.
So you're asking about this number here at the beginning?
Yeah.
So
Why
when
does it go to
the output is supposed to be 0 when you're in state 0, and you input a 1. So if I'm in state 0 and I get a 1,
would it go back to state 0?
oh, what happens if you're in state 0 and you get a 0? Is that your question?
Yeah.
I must have left something off. Just a minute. Oh, yep, you're right. So if you're in state 0 and you get a 0, the output is 0. And you stay in state 0. Does that answer your question?
But if you input 1 in, does it go to state 1 and it stays in state 0?
If you input a 1, I see. There. You see the error of my ways. There. If you input a 1, it goes to state 1 and outputs a 0. If you input a 0, it stays in state 0 and outputs a 0. I transcribed it wrong. Oops, my bad. Hope I didn't confuse anybody. So that's the input and the output. It's the answer to question number 5. So then, let's see what we got here. Let's try an example. Is everybody okay with this so far? Is this starting to come back to you a little bit? Let's try an example with toggle flip-flops. Because eventually what I'd like to do is I'd like to design a simple reduced instruction set computer using finite state machines, but I don't want to do that before you've had a chance to review and try and remember what it's like to deal with a finite state machine. So let's do this. We'll do a toggle flip-flop, T sub A, and another toggle flip-flop, T sub B, and a third toggle flip-flop, T sub C, and the output will be A, B, and C. And instead of drawing a complex circuit, what I'll do is I'll say the input to T sub A is equal to A or B exclusive or C. And the input to T sub B is equal to A or B. And the input to T sub C is going to be A or B exclusive nor C. Now, I drew a fairly complex circuit, but I'm assuming you guys can look at a circuit and figure out the Boolean algebraic equivalent. This is question number 6. and it's about a 3-bit counter, and it says given the following 3-bit counter, choose the correct state transition diagram by reverse engineering. Reverse engineering. How do I figure out what this does, given the design presented? What approach do I use? How about people in Zoom land? You're awfully quiet. Any ideas? No ideas? Really? Oh, with a truth table. Yes, indeed. Let's do a truth table. So I got A, B, C. Okay. And I got T sub A, T sub B, and T sub C. So I'm going to do what I know. I'm only going to write out what I know. If T sub A is equal to A or something, then all I have to do is write out the A part, which is right in through here. And now the rest over in here, well, that's going to be equal to B exclusive or C. And I know B exclusive or C is going to be 1, 1, 0, 0. And that's T sub A. Because I know the truth table for exclusive OR. Similarly, for T sub B, I know it's either A, which is over in here, or B, which is over here, and otherwise it's 0. So T sub B wasn't too hard. And so do people see what I'm doing here? Is it clear? You're not too confused by this, are you? Speak up if you are. No? All right, so then T sub C is equal to A. You can see where A is equal to 1. Or B exclusive or C, which is just like this, only inverted, because there's a little tick mark here. So what I'll do is I'll just go 1, 1, 0, 0. And that'll be exclusive. Yes?
1, 0, 0, 1.
T sub B. Oh yes. Oh yes. It should be the opposite of T sub A. So it should be 1, 0, 0, 1. Correct. Thank you. That is correct. That is correct. 1, 0, 0, 1. That's right. That's exactly right. I was copying this one, but I should be copying that one. That's exactly right. So now, given the remapped excitation table inputs, I can come up with the next state for A plus, B plus, and C plus. I know what toggle flip-flops do. Toggle flip-flops change. They toggle when the input is 1. And otherwise, they remain the same. They're in a hold state. So if the state is 0 and you're inputting a 1, next state will be a 1. If the state is 1 and you're inputting a 1, next state will be 0. It toggles. If the state is 1 and you input a 0, it stays 1. If the state is 0 and you input a 0, it stays 0. So the only thing the input does is it changes the state. So right in through here, I see there's going to be a change in the least significant bit. Here I see there's a change in the most significant bit. Here I see there's a change in the 2 most significant bits. So 0 goes to 1, 1 goes to 0, and this stays as a 0. So this becomes 1, 0, 0. Here I see change in least significant bit. That means both of these bits will be cleared. Is everybody sort of following along? I'm doing it in my head a little bit, but I think you guys know how toggle flip-flops work. You guys sort of remember? You put a 1, it changes. You put a 0, it doesn't change. So here it's changing every bit Here it changes every bit. Here it changes every bit. Here it changes every bit. So I take all these states. All I have to do is invert them. They're all going to change. Because you're inputting ones, that means 1 becomes 0, 0 becomes 1. Take the whole kit and caboodle, rewrite it, only invert it. So 1, 0, 0 becomes 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. Do it all at once. What do you think of that? Does it work? Work for you guys? It's good, right? Label your truth table. Always label your table. 0, 1, 2, 3, 4, 5, 6, and 7. Now I'm ready to answer the question. Finally, ready to answer the question. What does it do? Present state, next state. Right? 0 is the present state. Next state is a 1. Do you see it okay? Is it too high? Yeah, we'll bring it down just a little bit. I'm going to erase this. We'll do it again. So we're in state 0. Next state's a 1. We're in state 1. Next state is 5. We're in state 5. Next state is 2. We're in state 2. Next state is 4. We're in state 4. Next state is 3. We're in state 3. Next state is 0. State 7 also transitions to 0. State 6 transitions to 1. That's the answer to question 6. This is a classic reverse engineering question. We start off with a circuit diagram, which we reduce to inputs to our toggle flip-flops. Then we take the truth table, figure out what the circuit diagram means in terms of the truth table for the toggle flip-flop inputs, use toggle flip-flop characteristics to compute what the next state will be given the present state and the input, and then reverse engineer the present state, next state diagram into a finite state machine truth table, or in this case, a counter. Oh, and I got the right answer. I just checked. So that's good. That's good. Very good. Okay, who got confused by this example? Is everybody kind of okay with this? I'm just going through, this is like review from Digital Design 1. Who took Digital Design 1 more than a year ago? Show of hands. 1, 2. Are you scratching? Just 2? Who took it more than 2 years ago? So if you've gone a whole year without taking Digital Design 1, you probably forgot stuff. So it's okay to do the review, and it's okay to have forgotten. I mean, that's normal. And if you wanted to, you could go back and reread the book a little bit, and or watch some of the lectures. Right? Some of the later lectures will get you through some of this stuff. But if you got questions, I'm all about answering them right here, right now. So, and that's true also for you Zoom people. You Zoom people, and you know who you are. So let's see now. Let's do some more examples, interesting examples. Try and skip around a little bit because I think some of this is pretty routine. Now this particular homework is a little bit smaller than the other homework because it's only 16 pages. 16 pages. Trying to decide which one to do. I got another reverse engineering problem, but it's a little bit long. Just a little bit long. I don't want to do a long one. All right, here's one. You'll probably like this one. This is a Moore machine question. Suppose you're told that your Moore machine has 5 flip-flops, 3 inputs, and 9 outputs. What is the maximum number of states in the state diagram? So I have 5 flip-flops. 5. And I've got 3 inputs. And I've got 9 outputs. How many states do I have? Let's see. What's the maximum number of states that I can have? Maximum number. So this is supposed to be a Moore machine. Moore machine. So it's a Moore machine. Okay, great. Is it synchronous or is it asynchronous? Synchronous, because it's a Moore machine. That's great. If it's a synchronous machine, a Moore machine, and it has 5 flip-flops, how many states can it have? Let me do it a different way. Suppose it was a Moore machine and it had 1 flip-flop. How many states could it have? Let's do an example. Suppose I have state 0, and I can have state 1. It's 1, it goes this way. If it's 1, it stays there. If it's 0, it transitions back. And if it stays 0, it stays there. That's a parity detector. How many states does a 1 flip-flop Moore machine have? 2 states, right? Because it's either on or it's off. That's classic digital design, true or false, 1 or 0. If I had 2 flip-flops, how many states could it have? 4, right? 2 to the 2. So now I've got 5 flip-flops. How many states can it have? 32, 2 to the 5. That's it. See this part? It says the number of inputs doesn't matter. See this out part? The number of outputs doesn't matter. For a Moore machine, the maximum number of states you can have is dictated by the total number of flip-flops you've got. It's an integral power of 2. So you take 2 to the 5, that's 32. That's it. That's all you get. 32 states. That is a basic fundamental limitation of the Moore machine. You can't have more states than an integral power of 2 number of flip-flops in your machine. That's it. That's all you get. Now, let me ask you this. What is the minimum and maximum number of transition arrows starting at a particular state? Transition arrows. How many inputs does this machine have? Well, if x is equal to 0, it's transitions. If it's equal to 0, it's still transitions. There's only one input to the whole system, and it's shown on each arrow. But suppose I had two inputs, x and y. I could have 0, 0. And now I can do the same thing, only I can have different transitions when it's equal to 1, 0. Let's make it 0, 0. Same. So in other words, I had to double the number of transition arrows. In effect, what you can say is that if you have 3 inputs and 9 outputs with your 5 flip-flops, you could have 8, 2 to the 3 transition arrows, right? Because with 3 bits, any of these can be used in combination to transition you into or out of the state. So that means if you have 3 bits on input, you can make this into a fairly complex looking machine with only 2 states. And you can use those 3 bits worth of input to decide how you're going to govern the behavior of the machine. So with 3 bits worth of input, the number of transition arrows into and out of any given state is going to be 8. And that's the maximum. And that was the answer to question number 8 in homework number 2. How am I doing on time? I think we're just about out of time. I wanted to open the floor to questions in case you had any. Does everybody have like a copy of the book left over from when they took Digital Design 1? Yes? You have access to it? Anybody need a copy? You're going to tell me now because I can bring it in for next time or whenever. No? Don't need it? All right, well then I think what I'll do is I'll call it quits for now because my next question is going to take a little bit longer than I have time for because it's a complicated counter, complex counter. Yes? Homework 2, did you want it extended? Is that what you said? I think we'll make it due in about a week's time. So it should be due end of day Tuesday next week. But I wanted to fix the figures because I looked at this and I said after I printed it, the figures didn't come out. For some reason, the figures kind of came out blank. You can kind of see on the top. And I didn't like that. So it didn't copy right. I don't know why. So I'll try and figure it out. I'll fix it. Thanks a bunch. Stay safe. All right, yeah, let me turn off the recording here. Stop.